the last thing we did was how can we convert from exponential function or exponential expression to your radical item, right? So reminder, this is what we have is whatever our fraction is, our fraction, let's say if we have 7, 1/5. If we have 7, 1/5, reminder that the 1, this is our power, and the 5, this is our root. So it's always will be your power over your root, right? So if they ask you this item, how can you rewrite 7 raised to the 1/5 to become a radical expression? Well, the radical expression will be the 5th root of the 7 to the 1 power, but because it's a 1 power, we don't really need to write a 1 there, right? So again, it's always the power over the root. So in this case, this is what we convert to. And this, ladies and gentlemen, this is what we need to do in chapter 10.2 is how can you convert from one item to the next, or vice versa? How can you convert the other item to this item? So if you look at this direction here, they say that if we have something like this, let's say we have something in this nature here. Let's say if we have something like this, this is your radical. This is the 7 root. This is the 7 root, right? The 7 root of 5 to the 2nd power. So if we were to have this item and we ask you, how do you write this in a radical? I mean, rational exponent. So how can we convert this to a rational exponent? Reminder, this is what we need to ask yourself, or this is what you guys need to ask yourself is, what is your power and what is your root, right? So if we have this thing here, the 5 is the base as before. This is always your base. So your base is the same. So my base will be the 5 as in the base, and the power will be my 2nd power over the root, which is in this case, the 7 root, right? So no matter what I give you, no matter what they give you, for instance, they can give you the square root of x. And again, the square root of x, as you can see, if there is no power, then this will be our first power. So if you convert this to the exponential, right, exponent, and if you compare or convert this to the exponent, this is what we have is our base. The power is to the first power, and the root, reminder, if there is no number here, is that if there's no number here, then that assumed to be a square root. That's your base root. The base root that we have will be a square. Okay, if they have a number, for instance, if they have this number, if they have a 4, give me 1 second here. If they have this 4, and then let's say that something in this, let's do 3x. If they have this 4, then again, the 4 will be your root. And doesn't matter what inside here, because inside here, that is your base. So if we were to have this and they asked us to write in exponential form, the exponential form will be 3x, which is your base, raised to what is the power of the 3x? Well, the power of the 3x is 1 power over what is the root, and in this case the root will be the 4 root. So again, this is the idea of chapter 10.2. The 10.2 they ask you is, if we give you the radical, can you convert the radical to become the root? And if we give you the exponent, if we convert from radical to exponent, or if we give you the exponent, can you go back the other way? Right? So that's what you need to do, is you need to know how to interchange between the two. And the problem come in is sometimes they give you something like this, ladies and gentlemen. sometimes they give you something like this. Let's say it's the fifth root of 49. So no, the challenge part that a lot of you guys do, or sometimes if you do on your MyMathLab, and you say, oh, Mr. Tran told me that 49 is the base. So what we can do is we can say 49 raised to the 1/5. So yes, you can do that. And then when you type this thing in, they say that your answer is not in the lowest tone. And then you say, wait, how is not in lowest tone? Whatever we have is we have the power over the root. The reason why they say it's not in lowest tone is basically they tell you is, do you agree that the 49 is the same as 7 square, right? This two expression is the same. The fifth root of 49 is the same as the fifth root of 7 raised to the second power. And again, 7 raised to the second power is basically we see the 7 to the 2/5, right? Or if you look at this thing here, if you go to or remind ourselves for our chapter 5, do you agree that 49, well, not that, 49 is the same as 7 square? And if this thing were to be the same as 7 square, do you agree that in chapter 5, we have a power raised to the power, which is the power raised to the power? What do I do with the 2 power? Well, I can multiply, which is 2 over 1 multiplied by 1 over 5. And in this case, I know that 2 times 1 is 2, 1 times 5 is 5, right? So again, regardless of how you do it, this is what they want you to see, or they want you to recognize. If we have this item, you can convert to an exponent or vice versa. Well, first of all, question with any of this thing here, how to convert from radical to exponent. Now, if you don't have that, let me change the color here. If we don't have this, and if they ask us to rewrite now the other way around, if they ask us to rewrite this exponent to a radical, rewrite it to in the form of the radical. So if we were to, for instance, give you something like this, let's do 2 raised to the 2/5, right? If we have something like this, now if we have an exponent, and again, we did this, or we did this a little bit earlier, the power is the numerator and the root is our denominator. So if we know that the power in terms of this thing here, this is the 5th root and 2 raised to the second power, right? Raised to the second power, we can see that raised to the second power 2 times 2 will be 4. So again, I think they accept this answer. But again, they might also ask you this answer. But again, I believe if you wrote 5th root 2 to the second power, they accept that, okay? And the other thing they have is same thing go, right? They can give you something in this nature, let's say 10 raised to I over 9, right? So if we have 10 raised to 5 over 9 thing here, how can you convert this to your radical form? Well, we know that this is the 9th root, of the 10 raised to the 5th power, right? So 10 raised to the 5th power, which is 10 times 10 times 10 times 10, or in a sense, no, 10 raised to the 5th power is easy. We just add how many decimal we needed. Because of the 5th power is 10 times 10 times 10 times 10, 5 times, which is just 10, 100,000, right? But again, I think this is the one thing that they will ask you to do is to convert that, unless we have something in this form. Well, first of all, question to how to convert from exponential to the radical form. The one thing that you will see is they will give you something like this. Let's see. Um, and I think we did this last time, or we did this before. So to give you something like this, ladies and gentlemen, how would you convert this to your radical form? Well, we know that this is a cube root of 8 raised to the second power, right? Cube root of 8 raised to the second power, and I mentioned this to you guys, either take the root first or take the power first. We did this yesterday, and I will show you what we did yesterday. But if you do this thing here and you say, well, do you agree that 8 to the second power tell me that 8 times 8? And 8 times 8, do you agree that 8 times 8 is 64, right? We're using our elementary right? 8 to the second power, 8 times 8, 8 times 8 is 64. Now, what is 64 a perfect cube? And hopefully you guys see that 64 is a perfect cube in the way that, again, is 4 times 4 times 4. 4 times 4 times 4 is 64. And in this way, cube root of 64 is equal to a planar 4, right? And yesterday you didn't do this. Yesterday you did a little bit different. And this is the one thing about the exponent or the radical is they are commutative or associative, meaning doesn't matter which way you do first, right? Doesn't matter which group you do first, you still end up with the correct answer. So yes, it show you guys that we want to take first, because if you can take the root, it's easier to make a number smaller than to get a bigger number and then we stuck, right? So if you take the root first, everybody see that this is a perfect cube. The cube root, right? A cube root of 8, a cube root of 8 is equal to 2. And if it's a cube root of 8 equal to 2, well, what is 2 squared? Well, 2 squared tell me it's 2 times 2. And as you can see, doesn't matter how you simplify them, you still get 4 as your whole answer, right? And that's what they will give you a lot, ladies and gentlemen. They will give you something in that nature. Let's try this item here. For instance, they give you something in term of, let's say if they give you 4 raised to the 3 half, right? And 4 raised to the 3 half, if you see this item, first of all, if you convert this, and we know that this is a square root of raised to the third power, right? And if you remember 4 raised to the third power, or if you remember, we don't have to write a 2 here, because if there's no number, we know it's a square root. So if you look at this item, doesn't matter how you do item here, and again, if you see this thing here, you say, well, Mrs. Tran, I go ahead and I say 4 times 4 times 4. And 4 times 4 times 4, if you saw the previous problem, 4 times 4 is 16, 16 times 4 is 64. And what is a square root of 64? Well, a square root of 64, this is perfect square. So a square root of 64 will give me 8, right? If not, if you can see that this thing right here, this thing is a square root of 4 raised to the third power. And square root of 4, we know, or hopefully by now, you know a square root of 4 is 2 because it's a perfect. Well, 2 to the third power 10 times 2, and 2 times 2 is 4, times another 2 is 8. So as you can see, they are commutative. They are associative, right? Doesn't matter which way you do it first. The result is still the same. They are equal to 8. Some of you say, oh, Mr. Tran, I did not do that. I typed it in my calculator and I got the answer. And that's perfectly fine. Know how to calculator. You type in your calculator, you probably use that caret sign. There is a caret sign in your, and if you want to, if they ask you for a symbol, you can just say 4 caret sign and then 3 divided by 2. If you type this way in your calculator, you should see the answer is equal to 8 also. Okay, so doesn't matter which way. If they ask you a radical form, if you cannot simplify, then your radical form will be that item. Okay, and again, if we do in something like this, if we do something like x 4 over 4 over 7, there's nothing to simplify, right? There's nothing to simplify for this thing here because we don't. And if you have not, as you can see, this is basically the power over the root. The power is 4. The root is the 7 root. So question with this item here, ladies and gentlemen, any question in terms of how to convert from exponential to radical, or versus from radical back to exponential? Well, let's practice this item. We did this yesterday, and let's say simplify. The example we asked you is simplify. And let's say they ask you this item, simplify a square root of 90. So how do we simplify the square root of 90 here, ladies and gentlemen? So if you remember, again, this go to 10.3. If we have this thing here, basically we ask ourselves, is there a perfect square, right? Is there a perfect square? Is there a hidden perfect square in this number? Is there a perfect square in a 90? And again, hopefully you guys see that, oh, 90 is 9 times 10. But if you don't, do you agree this is one way to do is we can break this number down to our prime? And this is what we did, is we say as long as an even number, we can break it down by 2. 2 times 49 will give me 90. I no longer look at the 90. My 90, I rewrite the 90 as in 2 times 45. And since 45 divide that by, then you can do it by 3. And again, some of you guys say we divide by 5, that's fine. But again, if it's not by 2, we try it by 3, will work out. Again, instead of 45, I just say that 3 times 15 is 45. So basically, we just break down this number. And then 15, we know that 3 times 5. And again, as you can see, everything else, there's nothing else we can break down. So our goal is we break this item down, this thing down in a prime number. So we have a 2 times a 3 times a 3 times. And now if we have this thing here, we just ask ourselves, because it's a square, is there 2 of the same item? And because there are 2 of the same item, we can bring out one of them to the outside. And if we bring out one of them to the outside, do you agree that leftover The leftover, I have 5. So in this case, my answer will be 3 square root of 10. Okay, so again, this is what we have. And some of you guys say, well, Mr. Tran, I did not do all of that. I say 9 times 10, and then you are correctly, you are perfectly fine. And then you say, well, a square root of 9 times a square root of 10. If you remember the rule of multiplication, if they are together, we can split them out into 2. And a square root of 9 will give me 3. And it's just a 10. And again, doesn't matter how you dissect them. Doesn't matter how you dissect them. Everybody see that the answer is the same, 3 square root of 10. Okay. One way is we can break it down. The other way is, again, same thing go, right? And I put 124. If I ask you for a square root of 120, and I ask you, is there a perfect square in here? And if you say, well, there's a perfect square for 30, all right, perfect square 4 times 30. But let's say if you don't see that, right? 4 times 30, and I think that's it, right? But if you don't see that, we don't see the perfect square. One thing is, we know that we can break this thing down by 2. As long as an even number, out into 2. As long as an even number, we can break it down into 2. As long as an even number, we can break it down into 2. If it's not the even number, we try to break it down by 3. If we cannot break down by 3, we break down by 5. If we cannot break down by 5, we break down by 7, and so on and so forth. So whatever we break down, we don't care. We don't look at it, right? So this is the number we're looking for. The number we're looking for, if we break this thing down, the number we have is 2 times 2 times 2 times 3 times 5. And we say that this is the prime factorization. We have a 2, a 2, a 2, a 3, and a 5. And from this item here, because it's a square, we're looking for a pair of 2 of the pair of 2 of the same. They count of them, and the leftover we have on the inside is 2 times 3 times 5. And in this case, 2 times 3 is 6, times 5 is 30. As you can see, if we have a square root of 120, we can simplify to be 2 square root of 30. Now, different if we have a cube root of 120. And again, if we break this thing down, if we have a cube root of 120, the breakdown is the same. The breakdown, hopefully you guys see that the breakdown is the same, right? But the difference is because they ask us for a cube root, instead of finding only 2 of the same of the number and 3 of the same number, in this case, we have 1 here, 2 here, 3 here. And if we have a same 3 of the same number, what can go outside? Well, one of them can go outside. One of them can go outside, which is a number 2 can go outside. And if one go outside, my lonely 3 and my lonely 5 stay on the inside. And whatever stay on the inside is become a multiplication. So in this case, everybody see that we can simplify into cube root of, because it's a cube root, we're looking for a pair of 3, not a pair of 2. So a square root, we're looking for a pair of 2. The cube root, we're looking for a pair of 3. Okay. So let's challenge you guys. So this is where the problem come in, ladies and gentlemen. The problem come in is, let's say that we have, let me see. Let's say we have cube root of 80 x to the 4 Let's do actually 4 first. Let's start one thing at a time. So one thing is, hopefully you guys say that, ooh, 81, we square root of 81 is equal to 9. We know that because 81 is a perfect square. But cube root, why do I say because a square root, we're looking for a pair of 2. We got the pair of 2, so one of them go outside. But cube root, we're looking for a pair of 3, so 9 cannot go outside, right? So looking at this thing here, this is what you want to ask yourself for. This is what we have is, everybody see that we can break it down this way. I mean, we can break it out many ways. If you want to, let's break down this way. Many of you probably saw this way easier. Do you agree that 81 is the same as 9 times 9? You can disagree, but you will be wrong, ladies and gentlemen. And again, do you agree that the 9 is the same as 3 times 3? And the 9 is the same as 3 times 3. So looking at this thing here, see, this is what we have. 1 is 3 times 3 times 3 times 3. And because it's a cube root, we're looking for a pair of 3. So the pair of 3 is this, which is those are the pair of 3. And if it's a pair of 3, one of them can go outside. And the leftover, the cube root of the leftover, man, that's so many 3, right? The cube root of the one extra 3 on, okay? But let me take a look, or let's take a look at this thing here. Let me rewrite this problem. We did item here. We know that 81 is the same as this, right? 81 is the same as this. Cube root of 81, instead of say 81, we say 3 times 3 times 3 times 3. And instead of x to the 4, do you agree that x times x times x, right? X to the 4 is the same as x times x times x times x. And the reason why I write it this way, and you want to see is, again, because it's a cube root, in order for you to extract anything out, in order for you to simplify a cube root, you need to have a pair of 3 number. And if it's a pair of 3 number, this 3 can go to the outside, this x can go to the outside. And what is the leftover? Well, the leftover is still in the cube root. The leftover, we still have 1 3 here, and we still have 1 x here. And this bring us, again, this is our answer, is 3x, cube root of 3x. This bring us back to the item we did prior, in the sense of how many remainder we have. Okay, so in the same, this thing here, all of them together, they just put all of them together where the item is not a perfect cube. So let's try this item here. Let's say we have, let's try E. Let's try E here. And let's say cube root, and again, cube root of 32, x to the 7, y to the 11. Okay. So this is the challenge a lot of students. How simplify a radical where there's a number together with the exponent? You treat yourself as the basic of this. The basic of this thing is, we want to see what can go outside. And in order for you to take anything out, you need a pair of 3 because it's a cube root. So looking at this thing here, I don't know what the perfect cube is. You probably saw it. You probably saw that 8 is a perfect cube and 8 times 4 is 32. But let's say if you don't see it, right? Let's say you don't see that 8 is a perfect cube. Break down the number. break down the number as you've been breaking down. And if you look at this thing here, do you agree that 2 times 16 is 32? And say 2 times 16, say 2 times 8, because 2 times 8 is 16. And instead of say 2 times 8, instead of say 8, I can, and instead 2 times 4, I can break down the 4 to become 2 times 2. So as you can see, this is what we have, is we have 1, 2, 2, 2, 3, 2. We know that we see 3 of the same type, and 3 of the same type that can go outside. The I only have 2 of the 2. Again, the cube root, we're looking for a pair of 2. If it's a 4 root, we're looking for a pair of 4. Okay. So now, if you remember from last time, right? If you remember from last time, we can bring out a 2. And if I have x to the 7, what do I do with the exponent, right? What do I do with the exponent? No, if one thing is, if you remember, we can write it this way, and this thing here bring everything together, right? We can write it this way, right? We have 5 of the 2, which is the same as 2 to the 5th power. And do you agree that 2 to the 5th power, cube root of 2 to the 5th power, can we convert this to your exponential? Remember the power over root that we did in the beginning? The power over root, do you agree, or can we agree that we can convert this, the power is 2 over the root is 3? The power is 7 over the root is 3, and the power is 11 over the root is 3. We can convert, we can take this item and convert to the power over the root. And if you say, wait, how can we do that? Again, no, this is basically the same idea. That's cube root of 2 to the 5th times the cube root of x to the 7 times the cube root of y to the 11, which is basically 1 times each other. Okay. Why do I mention this item? Because if you remember way back in the beginning of this chapter, I told you that if the power is bigger than the denominator, if power is bigger than the root, we can simplify. And if we can simplify, there are some remainder, right? If we divide this, because it's a cube root, we divide by 3. And if we divide by 3, if we take this item here and we do the long division, do you agree that we have 1, the remainder is 2? And if we remember, this I told you is the whole number, and the whole number is the go to the outside, and the remainder is what left over, which is the power on the inside. And if you take the 3 divided by the 7, you can see that this is the 2, and 2 times 3 is 6, which is the remainder of 1. This is related to your x term. And if you take 3 go into 11 to give you 3 as a whole number, and 3 times 3 is 9, you have a remainder of 2. That's your whole number here. So looking at this item, what can you bring outside? Well, you can bring 1 of the 2 outside. You can the whole number for the term 2, which is you can bring x to the 2nd. The y, you can bring y to the 3rd. And what is the leftover? The leftover is you have 2 to the 2nd power, which is 2 times 2 is 4. We have 1x as the remainder here, and we have 2y as the remainder there. Okay. And again, I know that you say, some of you guys probably say, wait a minute, Mr. Tran, wait a minute. How do we find this remainder? How do we do this remainder, right? And we did this last time. But let's do one more without a variable. I mean, without a constant. And if you remember, This is our answer here for this particular problem. Let's take a look at one item, and this hopefully refresh your memory. Let's say x to the 17, y to the 23rd, z to the, let's do z to the 1. And put it out there, z to the 1 or z. So this one here, we don't have a constant. We don't have a number, right? All we have was the exponent. So if you see that this thing here, let me erase this thing here so I have some room. If you see this item here, and if you convert to your exponential, this is what we have is 23 divided by 3. And again, 1 divided by 3. So how do we simplify this item here? Well, to simplify this item, you ask yourself, how many x to what power can you bring to the outside? How do we know how many power of x we can bring to the outside? Well, we need to take this item and actually divide it. And if you divide this item, you can see that 3 going to 17 is 5 times, and 5 times 3 is 15. Therefore, I have a remainder 2. This is your whole number, meaning we need to take out x to the 5th power. Whole number is what you bring outside, which we can take x to the 5th power. And there is remainder. What is the remainder? The remainder is x to the 2nd. That is what on the inside. What about the y? What about the y if we take 3, go into 23? Well, we know that 3 going to 23 will give me 7 times. And in this case, we have a remainder, once again, the remainder of 2, the whole number of 7. Meaning, how many y can you bring to the outside? Well, the whole number tell me that I can bring y to the 7th power, and the remainder tell me that I have a remainder of 2, which is I have 2 to the exponent. Now, you say, well, what about z? Can we divide? Is there any whole number that 3 go to 1 is 0 times, and 0 times in terms of this thing here, 0 times 3 is 0, which you have a remainder of 1. So therefore a z is just, there's nothing you can bring outside because 0 exponent is just that item. So once we have this, that our answer is x on the outside, y to the 7th power, and again cube root of x squared, y to the 2nd, and z. And again, as you can see, all of the power on the inside is less than your root. Because it's less than your root, we cannot take anything out. In order for you to take it out, it has to be bigger than your root. Basically, the fraction is 2/3, 2/3, and 1/3. Question here, ladies and gentlemen. Let's try another one. Let's challenge you guys, and let's do G. And then we will take a look at the next set of easy problem. We have a 4 root with the 4 root, but let's say we have a 4 root of x to the 15, y to the 32, z to the 22. So the problem asks you is to simplify. And to simplify this thing here, basically in short, how many x can you bring to the outside? And yes, don't copy this thing down, but yes, technically you can do this, but again, you don't want, technically you can say, well, x time 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 x. We can say, I can write it out 15 times, right? I can write 15 times, I can write 32 times, I can write 23 times, right? But in the sense, why do I write that? Because of the root 4. Because of the root 4, everybody see that in order for you to take 1x out, you need a pair of 4, which in this case, I take 1x out. I need a pair of 4. This thing here, I take 1x out. I need a pair of 4. This thing here, I take 1x out. Meaning how many x I can bring it to the outside? I can bring out 3 of them. I cannot bring any of this thing out because I only have 3. I don't have 4. Everybody see that the elementary breaking down of this item is the root tell you in order for you to take one of them out, you need this many pair. That's the elementary of this root, right? But in, like I mentioned, yes, we can write it out like this. We can break it down like this. But if we have like 130 something, if we have, 32 is a lot too. I don't want to write y to the 32. I don't want to write 32y. I run out of space, right? Run out of ink. Not really, but I don't want to write that out. So this is the shortcut. And again, you probably say, well, it's not really a shortcut, Ms. Tran, if I don't get it. So, right, the shortcut is instead of write it out, this is basically, they tell you is take your root and divide, take your root and divide it by, take your power and divide that by the root. Take your power and divide it by the root. And if you take your power divided by the root, in this case, let's take a look at 4, go into 15. And that's where my 15 over 4 is. And if 4 going to 15, everybody see that 3 times 4 is 12. I have a remainder of 3. And this is the x value, right? The x value tell me that I can bring out x to the 3, and there is a 4 root. I still have the remainder of 3. What about the 32 and 4? Well, 32 and 4, do you agree that I can say 4 going to 32 is 8 times, and 8 times, there is no remainder. The remainder is 0, meaning there's no remainder, meaning every single y can bring it outside. Right? Your y, you have a pair of 4, meaning again, in order for it to go out, they need 4 of the y. You have 8 of them. 8 pair of 4. That's why y to the 8. And what about your z? Well, if you divide 4, go to 22, do you agree that 4 going 22 is 20 times, because 5 times 4 is 20? I have a remainder of 2. So in this case, how many y can go outside, or how many z? There are 5 z to, and what is the remainder will be z to the second power. And ladies and gentlemen, this is our answer for this particular problem here. So basically, this is what we did earlier in your problem. Is basically, I told you guys that the power over the root, which is all we do is we divide by the root. And if there's a remainder, it stay inside. So the answer is x to the 3rd power, y to the 8, z to the 5th, the 4 root of x to the 3rd, and z to the 2nd. Question here, ladies and gentlemen. Well, if you don't have a question, let's take a look at the next material. Let's pause with that for now. Let's take a look at, give me 1 second here. Let's take a look at one more example, or one more type of the item. And then we can call it a day for today. So if you look at this item here, so the last thing I want to cover for today is how do we add, or how do we subtract, or how do we multiply radical expression? Okay, so this is the last thing I want to do in terms of this material, and next week we will finish chapter 10. So in order for you to add, there are two things you need. In order for you to add, this is two very important things you need is you need the root to be the same, and you need the radicand, the number inside your root, to be the same. That's the two things you need to ask yourself is, do I have the same root? Meaning, do I have, if I have a square root, I have to have another square root. If I have a third root, I need to have another third root. Okay. If your root is the same, the must is the radicand, meaning the number inside your root have to be the same. And if the number one check, number two check, all you need to do is add or subtract the coefficient. Okay. Meaning combine the coefficient. So looking at this item here, for instance, if I have 4 square root of 5x plus 17 square root of 5x, do you agree that we have a square root and a square root? We're good to go. Do you agree that the radicand, the item inside your root is 5x and 5x? And if you have number 1 and number 2 checked, all we need to do is this item here. We take the coefficient, the 4 and the 17, which is the coefficient, you add them together, and this is what you have is 21 square root of 5x. Again, think about the square root of 5x is dollar, right? You have $4, you add it to $11 or $17. So in order for you to add, the units have to be the same. And again, I have $4 plus $17 in total, I have $21. So in terms of this thing here, I have 4 square root of 5 added to 17 square root of 5. I have in total 21 square root of 5. Similarly, for B, if I have 23 cube root of 17y minus 5 cube root of 17y plus 2 cube root of 17y, in total, how many cube root of 17y do I have? That's the question, right? If I take this much, subtract this much, and add this much, how many in total cube root of 17 do I have? Right, 17y to be exact. So if you look at this thing here, we see that the first item check, we have the same cube root to cube root. And the item inside my root is 17y, 17y, 17y. We are good to go. And if we're good to go, all we need to do is take 23 minus the 5 plus the 2. The cube root 17y will never change. You will never, ever, ever, ever can add the item inside your root. You only add or subtract the coefficient. So once we have this thing here, everybody see that 23, subtract 5 to give you 18. 18 added to 2. In total, you have 20 cube root of 17y. Okay. So again, in order for you to add, the root have to be the same, and the radicand, the item inside your root, have to be the same in order for you to add. And then you run into this problem. You say, Mr. Tran, my root is the same, but I don't have the same radicand. I don't have the same item in the root. So what do I do? What can we do? So if you look at this thing here, if we look at this, or if you look at this item here, let me share you the screen, and let's do it by I type out. If you look at this item here, let's do this item here first. So this is the problem I have, right? This is the problem that I have is 7 square root of 3 plus 13 square root of 27 minus 5 square root of 12. And you say, oh, Mr. Tran, that's my answer. The item inside my radical, my 3, my 27, and my 12, they are not the same. There's nothing I can do. Not quite, ladies and gentlemen. There is something you can do. There is something you can do, which is instead of saying that this is our answer, this is what you need to ask yourself is, inside 27, is there a perfect square? Inside the 12, is there a perfect square, right? So let's dissect this item here. Let's dissect the square root of 27. If you dissect the square root of 27, everybody agree that we have 3 times 9 and then 3 times 3. A square root of 27 is the same as, say, 3 square root of 3. I can take out one of the 3, right? I can take out one of the 3, and there's a leftover 3 in here. So given that, or after we do that, and let's take a look at a square root of 12. Well, what is a square root of 12? A square root of 12, do you agree that we have 2 times 6 and 2 times 3? Or in the sense, what can we write this thing as? We can write 2 square root of 3. So think about that, right? Think about that. Instead of write this item, and instead of write this item, I can substitute this thing in for that, and this thing in for that. So if I were to substitute in, my new problem will be this. My new problem will be 7 cube root of 3, because there's nothing here. I just bring that down. Plus I have 13 times, instead of say cube root or square root of 20, say 3 square root of 3 minus 5 times 2 square root of 3. And again, 3 square root of 3 and 2 square root of 3 is what I have over here and over here. All I did was I took the place of the square root of 27. I substituted back in, and once I did that, everybody see now, this is what we have, is we have 7 square root of 3 plus 3 times 13. 3 times 13 is 39 square root of 3 minus 2 times 5. 2 times 5 is 10 square root of 3. And if you see this thing here, and this is your challenge, and we will do this more next time, is challenge is they are, how can we make it the same? We cannot just say, oh, Mr. Tran, that's my answer, I'm done. We have to ask ourselves, we have to attempt and see if they are the same in this case. And this thing here, after you do one manipulation, the square root of 3 is the same for all items. So how many in total is the square root of 3 that you have? Well, you have 7 plus 39 minus 10. And again, you know that 7 plus 39 will give you 46. 46 minus 10 to give me 36 square root. In total, you have 36 square root of 3. Okay. Now, I know you are a little bit puzzling, but let's take a look at this thing here. If we were to have this problem, ladies and gentlemen, there is nothing we can do. Well, nothing we can do. This is our answer. Why we cannot do that here? Because this thing here is a square root. This thing here is a square root, and this thing here is a cube root, right? And again, one of them is a square and one of them is the cube root. they are different, we cannot do it, okay? There's nothing we can add or nothing we can subtract here. This is your answer. Your answer will be this. There's nothing we can do. And if this item, the other item is, for instance, if we have 9 square minus or plus 11 square root of 7, same thing go. There is nothing we can do. In this item here, this is my answer. There's nothing I can do. There's no way I can break this 7 to become the 2. I have the same square root here, but I don't have the same number inside my square root. So this will be the answer if we were to have this problem here, okay? So if we were to have this problem, this would be our answer, because there's nothing I can do to change the 7 to become a 2. And this 2 answer, or this 2 item, just tell you that if the root are different or if the radical are different, there's nothing you can do. And the problem that you guys will encounter a lot is when you have something like this. Let's start with an easy problem. Let's say we have something like this item, 5 square root of 7 plus 4 square root of 63. You say, oh, Mr. Strand, that's my answer right here, right? You just told me up here, if the item is not the same, one of them is 7, the other one is 63. If the item is not the same, I don't need to do anything. This is my answer, right? And again, this is the problem coming, is you have to attempt something, right? You have to ask yourself, can you, up here, there's no way you can make the 7 to become a 2. But down here, you have to ask yourself, is there a way that you can make this 3 to become a 7? Okay. And if you look at this thing here, and let me do it this way. If you look at this thing here, you can see, and most of the time, ladies and gentlemen, if there's a 7 here, you should be able to see that 9 times 7 is 63. And that's our goal is. Our goal is, how can we make this 63 to become a 7? And why do I say 9 times 7 is 63? What is the unique thing about this 9? Well, the unique thing about a 9 is the 9 is a perfect square. And if it's a perfect square, what can you bring to the outside? Well, if it's the perfect square, I can bring out a 3. And if I can bring out a 3, I multiply that item. Everybody see that we have a 7 on the inside. And this is your problem. You change the look of the problem, because 4 times 3 is 12. You change the look of problem, but you did not change the problem itself. And that is, how can you this 2 items the same? And if you make them the same, how many square root of 7 do you have? Well, we have 5 plus 12. 5 plus 12 to give me 17. Total of 17 square root of 7. And that's why last time we tried to ask ourselves, can we have we find the unperfect square? And if we can find the unperfect square, now can we add them together? Let's try another one. And let's say if we have something like this. Let's say we have 9 cube root of 24 minus 2 cube root of 3. So you will say, Mr. Strand, there is nothing clear. One of them is 20. One of them is 24, the other one is 3. And the two numbers are not the same. You just told me earlier, if the two numbers is not the same, there's nothing we can do. Well, I take it back. It's not that there's nothing you can do. The first thing you can do is you ask yourself, is there a way that you can break the 24 to become 3? Is there any way that you can convert that 24 to become a 3? That's the first item we have to ask ourselves, right? Last time, there's nothing I can do with the 7 to convert to become a 2. But now, everybody see that I can. There is a way that I can convert this 24 to become a 3. And what is this way? Well, do you agree? Do you agree that 24 8 3? And why do I use 8? Because hopefully you guys say that 8 is a perfect cube, right? Because 8 is 2 times 2 times 2, meaning I can bring out a 2. And what do I have? Well, whatever you bring it outside, you need to multiply. Well, there's nothing to bring it outside here. So again, this is what I have is because of the 8 is a perfect cube, and the perfect cube, I can bring out 2 of them. And this is what I have. I have 18 because 2 times 9, cube root of 3 minus 2 cube root of 3. And this, ladies and gentlemen, 3 cube root of 3 and 3 cube root of 3 is the same. We got it, right? We converted, we got it. And if we got that, what do? All we need to do is take 18 minus 2. What is 18 minus 2? Well, 18 minus 16, cube root 3 is the same. So if you have 2 of the cube root of 3, just think in terms that you have $18, take away $2, how many dollars do you have? So in this case, you have 18 cube, take away 2 cube root of 3. In total, you have 16 cube root of 3. Question here. All right, let's do one more and then we call it a day. Let's say 21 square root of 5 minus 7 square root of 20 minus 2 square root of 45. So let's say you have this thing here. And one thing I want to point out to you guys, looking at this thing here, and see the smallest number, right? The smallest number we have is a 5. And that's what you want to attack, right? That's what you want to attack, because your goal is you want to ask yourself, can you turn the 20 to become a 5, 45 to be a 5, right? That's what we want to attack. If you cannot do it, we don't need to do anything. But if we can do it, we need to change it, right? So looking at this thing here, the 5 will stay the same. Do you agree that the 20, I can convert the 20 to become 5 times 4? And again, the 2 stay the same. Do you agree that the 49, I can convert to 5 times 9? And why do we do this way, or why do we convert this way? Because again, our goal is we need the number inside your radical term. And also coincidentally, well, purposely, I make this problem up. Purposely, the 4 is a perfect square and the 9 is a perfect square. Is a perfect square and 4 is a perfect square. What can you bring to the outside? Well, this thing stay the same. 7 stay the same. Well, do you agree that the 4, I can bring out 2. The 4, I can bring out 2 of them. My leftover stay the same. I still have a 5 on the inside. Minus 2. And again, for the 9, what can you bring outside? Well, you bring out a 3. My leftover still stay the same. And again, this is where I have, and now to simplify this thing here, I have 21 square root of 5 minus 14 square root of 5 minus 6 square root of 5. And hopefully you guys say, magically, the square root of 5, square root of 5, square root of 5, those 3 items are the same. And if those 3 items are the same, all we need to do is take the 21 minus the 6. So what do I have? How many square root of 5? How many square root of 5 do I have? Well, 21 take away 14 will give you 7. 7 take away 6. Do you agree that you still have 1 left? And again, you can say 1 square root of 5 or simply just a square root. Question here, ladies and gentlemen. Question in terms of how they put everything together in this particular problem. All right. If you don't have question, let's stop here